Here we have a capacitor with a circuit and a neon bulb. Now notice how that neon bulb is blinking. Why would that happen? Today we're going to try and figure that out. To help guide your thinking, we'll give you some choices. Our friend Benjamin here will be helping you with your answer choices. Take a look at these. Now that you have your answer, it's time to do some science.
Science.
Let's start with A first. If the circuit were not complete, the light shouldn't be on at all. So let's try something. We're going to change the circuit a little bit. Notice how we're disconnecting the capacitor. You can see that the light stays on, which tells us that our circuit must be connected. In fact, it also shows us that the wires obviously can carry charge because the light is still on. Right, I know what you're thinking. It must be C. It's always C. It's the most common answer choice to be right. But is that really how capacitors work? Come on. You're killing me, Smalls. You're killing me. Wait, so you're telling me it's D? How is it D? I don't even know what D means.
Ho ho! I'm glad you asked, Timmy. Hey, my name's Paul. Of course it is, Tony. So now what I'd like you to imagine is that we're about to shrink down to the size of an electron and travel through this circuit. Get ready.
Hold on to your hats, kids, and keep your arms and legs inside the elementary charge at all times. Pay attention to how the electron moves, particularly around the capacitor. We'll talk about why this happens later. In this video, we're showing you the electron moving much faster than it normally would through the wire. Electrons are passing through each time the light blinks. Without this resistor, the light bulb would short out. Apparently, resistance is not futile. Thank you, folks. Alright, through the switch and back to the other side of the battery.
In order for us to talk about why the light bulb blinks, we're going to need to use our handy-dandy circuit diagram. In this circuit diagram, you can see that the switch, the battery, the capacitor, and the light bulb are all in the same position. Each of the individual purple circles are going to be some electrons that are in the wire. In order to show their movement, we're going to show some in yellow as well, though they are exactly the same electrons. Once we close the switch, the electrons are going to begin moving through the wire. Pay special attention to the electrons that are gathering on the negative terminal of the capacitor. Notice how they're bunching up. Well, once the electrons bunch up, they're going to create a more negative charge in that area of the capacitor. This negative charge forces the other electrons that are attempting to flow through the wire to go back against the current and through the other side of the wire in through the light bulb, thus causing it to light. Once enough electrons have passed through the light bulb to the other side, they stop gathering up as much on the negative terminal of the capacitor, allowing them to flow there again. This repeats over and over again, which is why you see the blinking light.
The material that's represented by the black bar in the capacitor is the reason why the capacitor works. Once this black stuff starts allowing charge to go through, the capacitor doesn't work anymore. Systems that work in this on-again, off-again fashion are called relaxation oscillators. Here, the repulsion from the negative side of the terminal creates an electrical relaxation oscillator. So each time the electrons discharge from the capacitor, they pass through the neon bulb and allow it to light up. Some relaxation oscillators are mechanical, like this one from Japan called the Shishi Odoshi. Notice how the water fills up just like the electrons on the negative plate of the capacitor did. Stay in school, kids.